and that's it.
Okay.
Okay.
Yes. And then the cubes, where do they come in? The 5 centimeter cubes?
Because that's going to help us later on, right? So when we do our reaction, we're going to do reactions with each of those cubes, right? And then so many other cubes are going to be used up if they react. And so the first thing is that we got to determine if they react.
Okay. That's why we are using the metal activity series, right?
What was that?
That's when we use the metal activity series, right?
That is correct. Yes.
Okay. I think I'm good with that. And then in question 2, when you ask about the amount of the precipitant produced, is it the amount in grams?
Yes.
Oh, okay.
Yep.
I think that's it for me. I don't know. That's about it, Dr. Henry. Thank you.
You're welcome. You're welcome. Any other questions? So does that help kind of get you started?
Yes, it does. A lot. So we choose the equations that react and calculate from there?
That's right.
Okay.
And then it also helps if you take a look down here. See. Yeah. So your little table, if I can move it, your little table down here, you figure out what is able to react. And then it also here, it says, okay, assuming that the metal reacts with solutions B, C, and F, but doesn't react with solutions A, D, and E. So that list up here, right? So based upon that, it should help you narrow down what your metal is.
Okay.
Okay? Okay.
Thank you.
You're welcome. Okay, Brenda. The other Brenda. See, hold on. Okay, so does that help you, Brenda? The other Brenda as well? Is that? Okay. Okay, any other questions? Man, I thought it was gonna be a hard question.
I think getting started was the problem.
Yeah.
How to start after that, I think it's just going to flow.
Yeah.
Yeah. Thank you, Dr. Henry. I think the rest of the questions I'm okay so far because we went through them with you last time.
Okay.
Yes.
Sounds good.
Thank you.
Well, you have a good rest of your weekend.
You too.
Okay. See, as for the project during the, so it's not included in that 20-minute presentation. It's its own independent time. How's it going? How's your presentations going?
It's going.
It's going.
Yeah, it's going.
Okay.
I think being stuck with guys, it's harder compared to ladies get things done.
Yeah, like, and especially now.
Yeah, Brenda is on top of things.
Yes.
Really on top of things.
Yes, you ladies are definitely more on top of things than guys are. And I've noticed that if you look at my class, most of my class has more. Most of my class have more women than men, and it's funny because the women typically do a lot better than the men do, and that's kind of weird because usually in science classes, for the longest time, it was the other way around. So, but Yeah, but it's definitely changed.
So yeah, it's going.
Yeah.
We're trying our best.
It's good.
Yeah. I see Alexis joined too.
Ah.
Alexis?
Alexis, are you there? Can you hear us?
Yeah, hello.
Hello.
How's it going?
It's going well. We were just talking about the difference between men and women in the class. So do you have a question?
I was looking at number 4.
Okay.
With the passing away of a young person with where the forensic officer goes in, and I was like Brenda was saying, it's kind of hard to get started on these problems.
Yeah.
And I think after that it kind of really helps you like just know what to do.
Okay.
So I guess the first thing it's asking to determine the molecular formula. So it's saying it gives you the 150 through 150 and 210 grams over moles. Is that what you're supposed to use to determine what it is?
It's no. So that's you're going to use part of it. That is not the only thing. There's more to it than that. So do you remember when we did percent?
Yeah.
The empirical formula.
I didn't practice it enough to like have it super retained and like step by step.
Can you repeat that, please?
Yeah, I do remember you going over that in the lecture. I just don't have it practiced enough to like remember exactly step by step.
Okay. So let's see if we can try to help that a little bit. Okay, let me shift things over.
So obviously combustion is just going to have CHO, right? That's all you're dealing with, those 3 elements?
Yeah. So we know that we're going to have a C. You're right. A C, an H, and an O. So that compound is going to have those things, right? Yeah. And then that's going to be reacting with, we know it reacts with what if it's a combustion reaction?
H2O?
Nope.
It has to combust, right? So
yeah. So then what does it need to combust? What does all fires need to keep going?
Oxygen.
Okay. And we know from a combustion reaction, our products are going to be
CO2.
Okay.
It's not H2O, is it?
It is H2O.
Oh, it is because of the evaporation
of water. Yep. Okay. So you always have to think of it. Combustion is always, you're going to get that evaporation. Like if we collected it, you would get condensation on the wall after a fire's happened, right?
Okay.
Yep. So we know that those are going to be your 2 products, right? So where's your carbon coming from? Where's all of your carbon coming from?
Isn't it in all living things?
But I'm talking about specifically for this problem. Do we get carbon from oxygen?
No.
No. So it's coming from our organic compound. So this is an organic compound, right? So all of our carbon is coming from here, okay? So, and we know that that's all going to be going to what product?
Oxygen.
It's going to be going to the oxygen.
You get CO2. You get CO2.
It'll be CO2, but it's not going to the oxygen. It's going to carbon dioxide, right? So all of the carbon, you have to think about it. Carbon is going to all of the carbon dioxide. So all of the organic carbon is going to be end up as carbon dioxide. And then all of the hydrogen is going to end up as what? In what?
H2O.
In the water. Okay. So we know exactly where the carbon is going. We know exactly where the hydrogen is going. And so if we know that, the first thing that we want to do is we want to get the quantity of those, right?
Yes.
Which we already have, right? Do we not?
I mean, yeah, you have. Are you saying for both sides or just on the product side?
Wait, what is
On
your
the
question?
product side.
Sorry.
I said, do we have the quantity of the carbon? Or
Yes,
can we figure out the
0.4.
quantity of the carbon? Yeah, we know that there's 0.45 moles of carbon dioxide. So then how much carbon is in that? And can I figure that out? So if I have 0.450 moles of carbon dioxide, how can I figure out how many moles of just carbon I have?
You divide it.
But divided by what?
We need
What is the
we need
relationship?
to figure out what is
It's grams
sorry,
over
go ahead.
moles.
What is the relationship between carbon dioxide and carbon? How many carbons?
Is it a ratio?
It is going to be a ratio, right? So, but
Yeah.
how many moles of carbon are in carbon dioxide?
12.
1.
Oh, I'm sorry. Never mind.
One.
12.
That's right.
One.
There's one because we have one. How many numbers do we have next to carbon?
One. None.
So for every 1 mole of carbon dioxide, we have 1 mole of carbon. Okay. And then that's going to give us the quantity for carbon. So we know that that's going to equal 0.450 moles of carbon. Now, what about hydrogen? So if we have 0.201 moles of water, what is that ratio of hydrogen and water?
Well, in this case, you have 2 hydrogen, right?
That's right. So for every 1 mole of water, I have 2 hydrogen.
So you have 0.402.
Okay. So now we know how much in terms of quantity we have of carbon, and we know how much in terms of quantity that we have of hydrogen. Okay. So if we take a look at this equation, where are we getting our oxygen from? Is it just coming from our organic compound, or is it coming from our organic compound and?
Well, you have 3, so you're combining both the organic and
So we're getting
O2.
the oxygen itself.
So we're going to be getting it from both parties, right? So from our oxygen supply, which is going to be unlimited, right? So we know that our oxygen is going to be totally unlimited. But we do know something else. It says the combustion of 9.002 grams of substance produces, right? So that means 9.022 grams of this is going to end up making our
Oxygen.
Well, it's going to end up making our oxygen as well as our carbon and our hydrogen, right? Because it's all together. So that's how much we have of our organic compound. So the law of conservation would say what? What we put in, we've got to get out, right?
So you would basically take the weight of all the oxygen and divide it by the 9.002 to see what that oxygen weighs?
Nope, because if you do that, you're going to, because remember, you have infinity amount of oxygen, right?
Oh, okay.
Because the air just has oxygen all over the place. But you're taking 9.002 grams of your organic compound.
Okay.
So if you know the carbon and you know the hydrogen, don't you know how much oxygen you have left?
Yeah.
Yeah, so you mean we have to add all of those two together and then subtract it by 9.002?
That's right. You subtract 9.002 by those two added together. That is correct. The mass of that, right? Because this is in grams.
But yeah.
Yep.
Right.
Yep.
Correct. I was just gonna ask you. So if it's a mole, we have to convert that to grams. How do we do that? What is 1 mole per 1 gram? Wait.
I don't know. How do you do that, Brenda?
It's the same thing. It's gram over moles.
Well,
right?
it says right here 210 grams equals to 1 mole.
You're not going to use that. But because think about it.
Mass?
Okay, so
We're going to use the molar mass. That's right. So we're going to use the molar mass of carbon for carbon because this is moles of carbon. And we're going to use the molar mass for hydrogen because this is how much hydrogen we have, right?
Okay.
Okay.
Let's see.
Is that helping you guys?
Yeah, you get 8.399.
Of what?
Oxygen.
Of oxygen? And how did you calculate that?
It's just the 9.002 minus the addition of both, which is 603.603, and it gives you 8.399.
Okay,
I don't know if I did it right.
Are we not changing the moles to mass first, to grams?
That's right. You have to change your moles to mass first.
Oh.
So you're saying for carbon, for example, we have to do 0.450 moles C, and then divide that by 12.011 moles of, which is the mass of carbon?
Well, you shouldn't be dividing it by it because we know that molar mass is grams per mole, right? And so grams is 12. So we want grams. We have moles, right? So this is moles right now. So this is 0.45.
Right. Oh, I did it wrong. So it's 12 grams per 1 mole.
That's right.
Okay, so I just positioned it wrong.
Yeah. So then our moles are going to cancel out. And then you guys should end up with what?
Yes. 1 mole. Okay. We should have 5.4 grams.
With the units, grams. That's right. 5.4 grams. Okay. And then for hydrogen.
Carbon.
If we're going to change that to
1.
Yeah.
So we know it's just the same 1. Because carbon is 1. So it's 0.421 grams of hydrogen. Which will give us.
Okay. So then we subtract it by 5.4 grams.
3.2
plus
what did you
0.402, right? You said 3.2 is what you got?
I believe so.
$3.198.
So I get 3.2.
Okay.
3.2. That's what I got as well.
Yeah. 3.2 grams, right?
It would be grams of oxygen, right?
Of oxygen. That's right. So now that you have your grams of oxygen, don't you need quantity if you're going to find the empirical formula? How would I get quantity?
Do you use the molar mass again?
We use the molar mass. So the molar mass of oxygen, right? So we have 3.2 grams of oxygen, and that's going to be divided by what? What is the molar mass of oxygen?
16.
16.
16.
Yep, 16 grams per 1 mole.
Dr. Henry?
Yes.
Do we multiply by 2 because it's oxygen?
Nope. Oh. Because we're just talking about the element oxygen right now, right? Because we're talking about the empirical formula. Okay?
Oh, okay.
We're not talking about the gas that's coming in. Okay? So if we do that,
it would only be 0.
Yep. So then that would be what? Isn't that like
0.2 moles?
Oh, 0.2. Yeah. Thank you. Okay, so we have 0.2 moles. Okay. So now let's go back here. 0.2 moles of oxygen. Okay. So we have, for carbon, we had 0.450 moles. For hydrogen, we had 0.402 moles. And then here we had 0.200 moles. Okay. So in this case, which one is smallest? Oxygen, carbon, or?
Oxygen.
Oxygen. So then in that case, we're going to divide all 3 of them by oxygen, right? So we're going to divide oxygen by itself. So we have 0. I'm going to put this in a different color to help us kind of keep things clear, if that's okay. So we have 0.200. Can you guys see that?
Yeah. Wouldn't that give us 1?
Yep.
So why do we have to divide it by the smallest one? Again,
because
I'm sorry.
We're trying to get the empirical formula because our goal is to try to figure out what the compound is, right? And if you guys remember, we need to determine its empirical formula, right? So if we have the empirical formula, we can figure out its molecular formula, right? We want to know how they compare to each other. How many oxygens are there in our compound compared to how many carbons there are in our compound, to compare to how many hydrogens there are in our compound. Okay, so we have to compare them to each other, right? So that's the reason why we want to figure out that number, because we want the empirical formula. Because we know it has a C, it has an H, and an O. We just don't know how many of each we have. That's what we're trying to figure out. Does that help?
No. I'm sorry. That was like a lot of information.
Okay.
I'm sorry.
So let me take a step back. Okay. So if I have a compound, let's say it's C6H12O6, right? So what is my relationship between my carbon, my hydrogen, and my oxygen in this compound up here in this corner?
6 carbons, 12 hydrogens.
I have 12 hydrogens and I have 6 oxygens, right? And that makes that compound, right? Because for this compound, which is sugar, right, glucose is always going to be C6H12O6, always. That's glucose, okay? So let's say I have another compound that is C3H12O3, okay? So that is a different compound. It always has that relationship. Since it always has that relationship, we can use what we call the empirical formula. So what happens is that when we use certain instruments, it doesn't give us the chemical compound, right? It gives us the relationship of each of the different atoms that are in that compound to each other. It tells me how many carbons I have compared to how many oxygens I have, compared to how many hydrogens I have. So if I talk about my empirical formula, the empirical formula is taking this number here, taking this compound, and find the lowest common denominator between those, right? So to do that is we divide everything in this case by 6. So we get
the smallest
C,
one.
yeah.
Oh.
H2, long as it gives us a whole number, right? O. And so this is what a instrument would give us. It would give us C, H2, and O. It'll let us know that that is the empirical formula, right? And so because it can't distinguish the actual formula, but it can give us the empirical formula because it does a relationship between each of those because it's limited by what it can actually do. Does that make sense?
Mm.
So what would be the empirical formula for what would be the empirical formula for this one?
Let's see. CH6O.
So 3 divided by 12 is?
No. 4. No, 4. Sorry.
That's right.
4. Oh, okay.
Okay, so the first thing that we're going to need to do is determine the empirical formula. And that's what we're doing because all it is doing a comparison of each of them to each other by dividing by the one that's the smallest. In this case, that was a 3 in this situation. So in this case, we're dividing by the number of smallest moles. So 2.2 is the smallest. So this would let us know that we have, in this case, we'd have 1 oxygen, right? So relative to each other, 1 oxygen. So then we take a look at our carbon. So we would go 0.450. We're dividing that by 0.2. And what is that going to be?
2.25.
Okay, so it's 2.25, right? Which isn't a good one. Okay.
Yeah, because what do you do then? Like you just
I'll show you. I'll show you here. I'll show you in a minute. So we're going to write it down 2.25, and then that's for carbon, right?
Yeah.
Okay. And then for for hydrogen, we know that it's 0.402 divided by 0.20. And that is
2.01.
Okay, so I'm going to tell you guys this, and it'll be brought up probably in class this week. So since this is 0.25, right? We want to try to get it as close to a whole number as possible. So what can I multiply all of these guys by to make sure that I get this guy close to the whole number as possible? A quarter, 0.25, which is a quarter. What do I multiply a quarter by to get $1?
4.
4. So I'm going to multiply everything by 4. Okay, so then my empirical formula is going to be, let's see, so 2.25 times 4 is what?
9.
Okay. Hydrogen. So this is already really...
Sorry, why are we multiplying times 4 again?
Because we want to try to get it as close to a whole number as possible, right? So like 2.0 is really, really close to a whole number, right? It's pretty much 2, right? But 2.25, that 0.25 is off so that we want to try to get it to a whole number, right? If it's anywhere between 0.2, if it's anywhere between 0.2 to 0.8, then we're going to multiply it to try to get a whole number. Okay, if it's 0.1, let's say if it ended with 0.1, you can just round to the nearest whole number. If it's less than 0.1, like if it's 0.01, then you could just round to the nearest whole number. So in this case, what we do to 1, we got to do to everything, right? So we multiply all of them by 4. So if we multiply the 2.0 1 by 4, what is that going to be?
0.04.
2.01 times 4 is 0.04?
It's 8.04.
Okay, so it's close enough to 8 to go ahead and use 8, right?
Yeah.
Okay, and then oxygen, we have 1 times 4.
It's 4.
Okay.
But do you still divide here by 4?
No, because
No, right?
look at the
It's an odd number.
Yes, because it only can be divisible by a whole, but it has to equal a whole number. It can't be equal to a fraction. And that's the reason why these guys have to be multiplied by 4, because it can't be a fraction, right? Because this here is really just 2 and 1/4, right?
Yeah.
Okay, it can't be a fraction. We need a whole number. So that's the reason why we have to multiply it by 4 to get a whole number. Does that make sense?
Yes.
Okay. Okay, so then this would be our empirical formula.
Sorry, let me interrupt you real quick. So the reason why you're multiplying times 4 is because by doing so, it will give you a whole number when it comes to 2.225.
That's correct.
Okay, so again, whenever we are in that situation, we have to kind of figure out, for example, you said the only reason we're doing that one on there is because it's 0.25 and not, for example, if we had, for example, let me just say this. How about if we had 2 instead of 2.25, if we had 2.05, we wouldn't have to do that?
That is correct. We wouldn't have to do that because it's so close.
Okay.
Yeah. Okay, so if you,
okay,
let me give you guys this. So if it's 0.2, let's say it ends with 0.2, it could be like 5.2, right? Or whatever number, and it ends with 0.2 to 0.8, right? If it's in that range, anywhere in that range, then you're gonna have to multiply it by a number to make it a whole number. Okay? If it's less than that, if it's like 0.1, then you don't have to worry about it. Okay? So like, let's say if it's 4.1, right? Then we could just use 4 because it's so close to 4 that we don't have to worry about it. Okay? And I'll give you another little sheet to remember this by. It's right on the side.
And the decimals always have to equal a whole number. So the 0.8, you would multiply it by 5 to get 4.
That's right.
It can never be like like the main one that you're trying to convert. That one can never be a decimal. It always has to be whole.
Yeah, so they all have to be whole numbers. They can't be decimals because
but I'm just saying like the hydrogen was, but it was so minimal that it was able to be rounded down.
That's right. It's so small that you can just round it down. That's correct.
Okay.
Yeah. Yeah. That is correct.
So then we have C9H8O4.
Yep. So that would be the empirical formula. Yeah. Okay. So now that we have the empirical formula, we can sit there and calculate its molar mass, right? And if its molar mass is between 150 and 210, then we know that is the formula that we're looking for. That it's also its molecular formula. If it isn't between there, then we need to multiply it by something to get that molecular formula. Does that make sense?
Yeah, so we would have to take each.
Okay, so let's try it.
Okay.
Yeah, we just
so multiply 9 times 12 and then 8 times 1 and then oxygen 16 times 4, right? And then let's see.
It is between it. It's 180.
Okay, so then that would be its molecular formula. So that would be your answer.
Do we have to show that in the test, the multiplication of each?
Yeah, you should show it, yes.
Damn, that's a very long problem.
Yes, it is. That's why this is a take-home test.
I would have never figured it out myself. Good thing I joined it right when you guys were touching it.
Okay. So then the next part is we want to put this into our Google or whatever program, and we want to see, it says, identify a common household drug that may have been, let's say that might have been in the young man's bloodstream. Okay. So then you're looking for a common household drug. What was that?
It's based on those chemical compounds?
Yeah, it's based upon those formula. Yeah. So this is actually what this is actually done, like in terms of forensics. So what they'll do, they'll take the bloodstream, they'll run the sample in there, and then they have things that are normalized. So they'll identify, just the standard stuff that's in blood and everything like that. And then there'll be the anomalies, and they'll take those anomalies and they'll sit there and say, oh shit, this is an anomaly. And then they'll isolate it, and then they'll do another study, another run on it,
So we're not doing
from that, then they can sit there and say, well, he OD'd on heroin or, on whatever drug it could be.
So can we Google, for example, the household drug of Tylenol?
So you say it's Tylenol?
What do you mean?
You take this chemical formula, right? And you plug it in, and you look at something that's a household drug, something that somebody may take commonly,
It's aspirin.
Okay.
How do you figure out the name of the formula? If you didn't have Google, how would you figure out that it's aspirin?
Well, see, that's the thing. There's
wow. Good job.
Figure out if we didn't have Google, right? If we didn't have Google, the old-fashioned way would be you'd go to this index of all of these chemical formulas or the different names, and you'd look at it and cross-reference it.
So we have this case, so in this case, it's okay to look it up in Google?
Yeah.
Okay.
And so that's the part of it, and that's part of the reason I gave you this test, is because there are times it's okay to look stuff up in Google, right? And you just want to confirm it, right? And then there's times that you don't want to look stuff up in Google.
Right. So B is just asking for the name of the drug. That's it.
That's right.
That's it.
And we just determined it is
aspirin.
Okay. Aspirin.
There's no easy way for forensics to do this. Like they have to do all this math.
Yeah.
Well, now there's computer.
They have computers to do it for them.
There it is.
But you guys need to be able to do it without the computers, because you don't know, you got to always confirm it. You're going to make an assumption. This could change somebody's life, right?
Yeah.
You're saying this guy was murdered, right? Based upon your data, and stuff like that. And, you may find out that he's just allergic to aspirin, and that was the problem. Right.
Yeah.
And he's like, do I have to do all this math to get the answer? Yes, you got to do all this math to get the answer.
No, I was just wondering, like, I'm sure they had a simpler form. There's no way stuff would get held back so much.
But look how quick you guys did this. This was less than an hour.
Yeah, but there's
less than an hour. Still.
There's a lot of people that are dying. Multiply that hour by how many dead patients you have, and you have weird substances that you have to do.
No, so in the lab itself, they have references, and so if it's a poison and everything, they'll send it through their toxology screen, and so they'll send it through a couple of assays, and the assays typically they take about 45 minutes at the most, 20 to 40 minutes, and so within 20 minutes you'll know. It'll go through the database compared to what they have and highlight the ones that they believe it to be. And so if it's somebody who's taken a poison, they'll give you a list of antidotes or antidotes that would kind of work on a couple of them that they could use, to neutralize or at least slow it down. Does that help?
Yeah.
Any other questions? That's going to be 50. We'll give you, that's 20 minutes of your guys' time, though. Because I gave you guys a lot of help on that
Wait, what's this deal? I wasn't here when that was specified.
I know. I just proposed it now.
Oh.
Wait, what was it?
I said that's 20 minutes.
Did you guys go over any other questions?
We did. We went over we talked about one.
Oh, I know. What? So you're telling me I missed one?
Yep.
Dr. Henry, for number 5, for all those, you're asking like the specific type of bond. You're saying if it's ionic or covalent. That's it.
Yes, and then remember, sometimes I'm not talking necessarily about bonds, but I could also be talking about interactions that are referred to as bonds.
Okay.
So if we want to go over and say, you can say if they're wrong.
I'm not going to give you the answer.
No, my question to you, I mean, for example, Ag, that's just an element.
Okay. But what type of bond would that be?
The bond?
Yeah, it's a metal, so it would be a metallic bond.
Metallic bond.
Gave her the answer. I'm sorry.
I thought that was just a cloud. No, it's okay. Wait, no, it's not okay.
But I don't know if that's right either. I mean, I put metallic bond. I don't know if that's right.
But is that it's actually a bond? There's a bond. I thought it was only ionic or covalent. Those are bonds. But when it's an element itself, I didn't think there was a bond.
Well, that's what I thought too. But it's like you have Ag and not. It's just an element.
Okay, so let me look at this. Silver. Okay, now silver, does it connect to each other? Like you have a silver ring, isn't that one big old ring?
Yep.
Is that one big piece of silver? Is that one element of silver?
Yeah.
So we know.
No, I mean it's multiple.
Yeah. So then, how is it connected to each other?
I mean, with bonds, but I just didn't know that
Thank you. It's connected by bonds. Everything is connected by bonds, right? In some way.
Right.
Pretty much everything.
But okay, so we didn't go over.
Yes,
right.
we did.
I mean,
we did go over metallic bonds. We talked about metallic bonds. We talked about ionic bonds. We talked about covalent bonds. We talked about, to be specific, we said polar covalent bonds. We talked about, and I can tell you the chapter too. You want me to tell you the chapter? It's chapter 12. Look at your notes.
No. I don't recall going over the metals being combined together, but they can only be combined. No, because obviously there's many things that are mixed. So no.
Take a look at chapter 12. So I'm gonna say, but I'm not saying anything. You guys said it, and you should be confident in your answer at this point. There's no waffling that you guys are doing. So stop the damn waffling. That's what I'm saying.
So your remember the type of interactions would it be with B and D, because obviously well, B is a type of bond, but then D would be like that interaction, right? That's occurring.
Okay, I'm not saying anything. That's what you're saying, right? And then you have 4 people here that you could either talk about this with, or or not.
Okay, say it again. For D?
Yeah, I was just saying because he said, remember, it's not just like the type of bonds, it's also the interactions.
That is also named a bond.
That is also named a bond, yeah. So, you have covalent, and then you have ionic, and then metallic. So B and D are the same element, but B,
they're interacting with each other.
No, I would say B is like the type of bond, and then D is the interaction between that is occurring with those, like the polarity and all that stuff, right? I don't know.
But D is also interacting.
What did we talk about today? I mean, this week.
In the lecture?
No, not in the lecture, in the lab.
Oh, the polarity, miscible, immiscible.
And then we're also talking about interaction. And
I also said IMF.
Yeah,
what does IMF stands for?
Intermolecular forces?
Intermolecular forces. So I would probably look that up in the book, look it up in my notes.
Oh, you did tell me about it too.
Oh, is that what you're
asking? We talked about there's dispersionary forces, hydrogen, intermolecular forces.
Hydrogen what? Come on now.
Hydrogen bonds.
Oh my God. Becky. An interaction that has a name of a bond. Oh my God. Is that just a coincidence or something?
Wait. So hydrogen bond, I thought you were asking like for dipole or London dispersion.
No, it's asking you for the different types of bonds, right?
Oh, okay. So
isn't that what it's asking you? It didn't say anything about dipole, right? It's talking about.
I was just saying because you said IMF.
Yeah. So. Yeah, IMF are the intermolecular forces, right? Yeah. And hydrogen bond is an intermolecular force.
Oh, that's right.
That's right.
If it has all three, though, or two, or not just one, is it like what?
Yeah, but
there?
if you look at what you have here, right, you don't have all three, right? The first one is an example of what?
Ionic.
You're talking about A, right? Ionic bond.
Yeah. The second one is an example of what?
Covalent.
What type of covalent?
What's that?
What type of covalent? Because there's two types of covalent.
Polar covalent.
Polar covalent. Okay. The third one is an example of what?
Metallic bond.
Okay. The fourth one is an example of what?
The hydrogen bond.
The fifth one is an example of what?
You said the fifth one?
Yes.
It also looks like a hydrogen bond.
Nope.
Actually, no.
Well, you're saying that it's pulling away from each other, and that's what the arrows are showing, right?
Yep.
So that would be non-polar.
Okay.
I just don't know if it's
what?
Covalent bond.
Okay.
That's it?
That's all. You guys really wanted to make it really, really hard, right?
Well, it's confusing, man. It's just you have all these possibilities. You have
name the specific type of bond. That's all. That's it. It's nothing else. That's all it's asking for. So don't make shit up. Don't make it harder than what it needs to be. It's asking you for this specific type of bonds, and you guys just did that, right?
It's just as a student, it's like you have all this information and you second guess yourself, you know? Like,
exactly.
What if it's...
But that's what I'm trying to get you guys out of the habit of. Read what the question is asking you, right? That's all I'm asking you. I just want the specific types of bonds. That's it.
And then okay, you got to think like we're coming out of an hour-long problem. You're like psychology.
Exactly.
You're doing psychology.
That's the best part about this exam, right?
You throw in a 2-minute problem.
Some of them will kick your butt, and then some of them are just like, here's the present for you, right?
Yeah, it's just weird. You know, you come out of this 1 hour and then you throw this curveball and it's like a minute problem and you second guess yourself. You're like, no way, that's just it. You know?
It can't be that easy. No, it can't be that easy. He's an asshole. It definitely can't be that easy.
I didn't say that. Oh man, definitely tea time in here.
Okay, so the rest I'm gonna let you talk to some of the TAs about on this exam. So
I have
or you guys could talk to each other about it because you guys are doing pretty good. This is like a good team here. You guys should exchange each other and meet each other on Zoom or something.
Is everybody here from Hartnell?
Because we're always like,
yeah, everybody here is from Hartnell.
Well, I'm from.
Like you guys
right?
are not born in Hartnell. Even
That's
though
a
it feels
funny
like
one.
it sometimes.
Or do we have anybody? Yeah, I
You
think
never know.
everybody here is from Hartnell.
Yeah.
Okay. In regards to the lab, Dr. Henry.
Yep.
I mean, not that I want to talk about the testing. You say we have to talk about it with the TAs now. So we can't ask you any more questions about the test?
You can ask me one more question about the test. But it can't be, how do I get started?
No, it won't be number 8. I think I got that one.
So I'll let you guys discuss the question that you guys want to ask. So plan it out.
Okay. Is anyone having a hard time with the rest? Hello.
I'm looking.
I know, me too.
Dr. Henry, just in terms of like definitions, precipitant is what we saw with that in that lab, right? Where you have a liquid form and then the bottom of it kind of starts sinking up and it looks like it's almost
separated. Right. It gets sticky and you start getting stuff that drops out at the bottom. So it forms a salt. Yep. So anytime that you see the word precipitate, it means that you're forming a solid.
Right. So like in a formula that would switch, right? No matter what it was in before, it would turn into a solid.
Yep. Yep.
And it doesn't matter anything that's attached next to it after that.
What do you mean?
I mean, I don't know if this is existing, but like, I don't know. Let's say you have a formula. I don't know exactly. I don't have one on the top.
Right on my board. Give me an example.
I mean, I don't really have. Okay. I mean, I don't know if this is an example of that specific. Like I don't know. I can't even. AG.
Here, let me see if I can help you out with some things. Okay. So since you guys are here, I'm gonna throw some bones to you, right? This is gonna count as your question.
Wait, what? No, I wasn't trying to do I wasn't trying to do that. I'm just
asking. Still no, I know you're trying to do it, but I'm trying to help you guys help yourself, right? Okay, so if you guys go to your packet, I'm gonna pull up something real quick. Let's stop sharing. Oh, I find it. And then we'll blame Alexis for it anyway. So.
I was more asking.
Hey guys, since you guys were here for like chapter 1, can any of you guys stay and actually help me with number 1? Since he went over it already. I was kind of late. Sorry.
I joined maybe in the end of it. I forgot who it was that was here talking to
Brenda.
Dr. Henry.
Brenda squared.
So Brenda. I don't know what she said.
Okay, so this is a solubility table.
Yeah.
And what it means is, let me blow it up. Can you guys see my screen?
Yeah.
Okay, you guys should have this in your packet, right? Okay, so if we have aluminum and acetate coming together, meaning that they're forming that product, aluminum acetate, if it's here in the orange, that means it's going to form a precipitant. This is called slightly soluble because most of it is going to be a precipitant, but if you put enough energy into it, a whole bunch of energy into it, then you can make it into, it can go into solution. But if you don't, it's going to form a precipitant. So that's the reason why it's going to be exactly a solid. Yes. Okay. If we have barium and carbonate, that is also going to form a precipitant. Okay. So anything in pink is going to form precipitants. Okay. If it's in green, that means it's soluble. So when it's aqueous, it's going to dissolve just like salt does. Okay.
So it would be AQ, right? Not liquid.
That's right.
Okay.
It wouldn't be liquid. It would be AQ. That's right.
And then decomposes like aluminum.
If it decomposes,
sulfide.
If it decomposes, then you're not going to get a product from that either.
Okay.
Because it decomposes.
Right. And then soluble hydrate, that's like where you have like 9H2O.
Yeah, if it hydrates. Oh yeah, you're saying here. This one says that.
Yeah.
No. So this makes reference to if you have the hydrate, it's soluble. But if you don't have the hydrate, it's not soluble. It's hard to dissolve.
So if it's not soluble, it's a solid?
Yes.
Okay.
Yeah.
Okay. So it needs that H in front of it.
No, not the H in front of it. It's times water, right?
Oh, yeah.
Or if you're pulling them together to make a solution, right? Then it's always going to be soluble because it's always going to have that water present. It's going to have enough of that water present.
Dr. Henry?
Yes.
Now, when it comes to question 2, and we have to write the ionic equation.
The total ionic equation. We'll be talking about this week.
Yes. Now, I'm wondering if copper sulfate is soluble and ammonium nitrate is also soluble.
Yep.
So
then that basically
the equation just cancels.
That's right. You're not going to get anything. So you're not going to get an equation.
So they're all spectators?
Yep, that's right. They're all spectators.
Oh, so does it mean when okay, question D says determine the net ionic chemical equation, it means there's no answer to that?
That's right. You will put no reaction. So NR.
Oh, okay.
NR stands for no reaction.
Thank you.
That's it. So did you guys get that?
You said determine the net ionic chemical equation. It's non-reactive because if you base these...
Okay, so I'm not going to explain it to you because that's not fair. I want Brenda to explain it to you because Brenda is the one that figured it out. Brenda, let me pull up the question so then you can explain it to the class. What's going on? Now you guys have to put...
Thank you, Brenda.
Oh my God.
Let me find the question. Question number 2. It's worth 20 points too. So you better write this down.
Oh.
I'm gonna step away from the table. You guys can discuss.
I'm ready, Brenda. You got this.
Oh my God, I've never done this before, so bear with me, please.
Hold on.
Get it big enough that you guys can see.
It's the next page, I believe, Dr. Henry.
Oops. Sorry. There we go.
No.
Yeah.
Okay.
Right?
Thank you.
So
yes, number 2.
So in this case, we have to write the chemical equation first, just the normal chemical equation. That's what I do. Right. And in this case, we have ammonium sulfate, this. which is reacting with copper 2 nitrate.
Brenda, what type of computer do you have? Oh, you can write. So you already know what you're doing. Okay. So I'm gonna chill. I'm gonna mute myself and then go and find my beer. So okay, so I'm gonna let you finish doing what you're doing.
So ammonium nitrate is what? N, I think N.
NH4 and then CO4. But
NH4 into brackets 2, right?
Yeah, 2 because it's a -1 charge.
Oh my God. How do you do this, Dr. Henry? 2 SO4. Oh my God. Does anybody know how to do this?
Yeah, class? I could write it.
Yes, please do.
Ammonium sulfate with.
What's the charge? 2?
Copper.
Yeah.
2.
So it's NH4, NH4 into brackets 2, SO4.
Give me a second.
Yes, the charge is 2 minus, so yes. Copper 2.
Okay, so I should be able to annotate. Oh, sorry. Okay, so you have ammonium sulfate, right? Which is NH4 in parentheses, and you put a NH4. 2, and it has a sulfate, which is SO4.
Correct.
Okay, and then the SO4 has a -2, and this has a +1. So you need to multiply this by 2 to balance it out, right?
No, it's okay the way it is.
You're right. So the reason why we're putting the 2 on an NH4 is
to balance it out.
Yes. Yeah. So it's already balanced out. Plus, so it would be plus Cu, copper, parentheses NO3, parentheses 2.
Yeah, because the copper has a 2 charge. Yeah.
Yes.
Okay. So
the products.
Oh, the product, yeah. So did you use
so it will
this
be
is a double displacement, right?
Exactly. That's the answer for the first question. So, the type of reaction.
Yeah, so A is double displacement.
Oh.
Mm-hmm.
I know this because that's what my presentation's on. So then that converts, right?
Yeah. So it will be ammonium nitrate and copper sulfate.
So it would be ammonium NH4 and a NO3 plus SO4 Cu or CuSO4?
CuSO4.
CuSO4. SO4. And then
NO3
NH4 NO3.
So look, the way I learned this is these are your cation ions. I mean, not cation ions, your anions, right? Is there a negative charge?
Mm-hmm.
And being that these
I always just put the numbers once.
Yeah, the negatives always switch places. So these two negatives are gonna switch places. So then you have you said it's NH4.
NO3.
And then NO3 comes over.
Plus.
And then yes, the copper stays.
Cu SO4.
SO4. And then you check if this is balanced.
Balanced, yeah.
So NH4 has a plus and NO3 has a minus, so that's good. And then this has a 2 charge and the SO4 has a -2, so that's balanced, but it is not balanced over here, right?
So you have to put a 2 in front of the ammonium nitrate.
This one right here.
Yeah. No, sorry,
no.
ammonium nitrate. That one is fine.
It would be on the other side.
NH4, NO3. You put a 2 in front of NH4, NO3.
Okay.
So awesome.
The product side. Yes.
So this gives you 2, that gives you 2, that gives you 2, that gives you 2. Okay, yeah. Okay.
So we've already answered question B. A and B we have answered. So C, the total ionic equation. Now, like you were saying, Alexis, the anions and cations. Now in the ionic equation, you have to separate like the ions, like the NH4 separately plus SO4 plus Cu 2 plus. You get it?
Okay, can you slow down? So it would.
Give me a second. Okay. I'm writing down the
Sorry.
equations. So,
I got lost on that one.
So for B, you're gonna write the balance equation, right? So it's NH4 times 2,
which we
SO4.
already did.
Yeah, we've already done that.
Okay. And then you're saying for C, you gotta separate.
Yeah, you have to separate each ion as it is. Like now the anion and the cations separately.
The product side or the reactant side?
Oh, the whole equation.
Okay. All right. So
it would be NH4.
NH4, then you put the ion plus on top.
Okay, so we NH4 plus.
So the greens
because
are your
it doesn't have.
So I'm drawing green arrows, and that represents the cations, which are the plus. Okay. And then the blue arrows represent the anions. And you're saying to put all the blue arrows together.
No. You write this equation as it is, right? But now you have to separate each ion. You have to say like NH4, you put two NH4 plus SO4 plus Cu 2 negative, sorry, 2 plus, then NO3, 2 NO3, 2 negative.
Sorry, I think you're going pretty fast. So go back. So you have to do NH4 plus NH4 plus
No. You don't have to write NH4 twice. You just put the 2 in front of NH4. You say NH4, 2 NH4 plus. Then you put the plus. You say plus SO4, 2 negative, right? The ion SO4 has a 2 negative charge, right?
Correct. Okay.
So then you say plus the Cu, the copper has a 2 plus charge, right?
Yes.
Then you add again, you add the NO3, which has a negative charge, right?
And a 2 in front of it.
And a 2 in front of it, yes. Then you do the same for the product side.
Do you have to put the negative charge?
Yes, you have to, because it's an ionic chemical equation.
Okay. So NO3 has a -1.
Mm-hmm.
Yeah, 1 minus.
Nitrate has a minus.
You left out the plus for the ammonium ion.
Oh yeah. Here, sorry, I'm running out of room.
So for the ionic chemical equation we have, that's just writing all the ionic formulas, right?
Yes.
Which are those. How do you know copper is ionic?
Because and now when you're writing the ionic equation, you have to say they're in aqueous, the AQ down here, because they're in solution. When it's ionic, it has to be in solution.
Okay, so all of them are aqueous?
All of them are aqueous, yes. So what happens?
Is aqueous?
Mm-hmm.
And then this is aqueous.
Copper.
This copper and NO3.
I thought it was a metal. Copper is a
metal.
All
of them are aqueous.
Yeah, because it's in solution, right?
Yeah.
That's an A, by the way. Sorry, AQ.
So what I was asking Dr. Henry, in the case where they solidify, for instance, let's say like copper sulfate became a solid, is insoluble, then that would be the net ionic chemical equation. So you would have chosen the copper plus the sulfate to make copper sulfate. That's if it's not soluble. But now, because all of them are soluble, it means we do not have the net ionic chemical equation. But in the case where you have one that is insoluble, where it makes a precipitate, then whatever it is you get in solid form, that is what you're going to use to make the ionic chemical equation. Otherwise, everything else cancels out. Did you get it?
When you, sorry, since I was writing it on the board, I ran out of space. For C, you know how we got to the 2NO3 at the end of the reactant side? For the ionic chemical equation, do I draw the arrow?
Yes, you draw the arrow and you put the other part, the products part, because it has to be like a chemical equation. So you have to put the products part as well.
Okay, so 2NH4. That's a plus. So the 2NH4 has a 1 plus, right? And then the plus NO3.
So for the products, it's 2NH4 again?
Yes. Oh, there's no. Yes, it's 2NH4. You're right,
okay.
Alexis.
So on the first one.
On the first one, there's 2. That's why it's balanced.
So 2NH.
2 is to 2.
Plus NO3 negative.
So in this case, all the ions cancel each other out. But if you were to get a precipitate, if one of these products was not soluble, then the ionic equation would be different, because the insoluble one would remain in solid form. So you would not change it, if that makes sense. Let's assume copper sulfate was insoluble, for instance. Then in this ionic equation, the first part would be right. But when you're doing the products, you do the 2NH4 plus and the 2NO3 negative, and then the CuSO4 remains in like a solid. So you just write it CuSO4 solid, if it was insoluble, that is. Then the answer to D, if CuSO4 was insoluble, was a solid, then the answer to determine the net ionic chemical equation would be SO4 plus Cu to make CuSO4. But now, since it's soluble, there's no equation to write. It becomes, everything else cancels out because everything is in ion. The ions cancel out, if that makes sense.
So you would just write non-reactive?
No, there's no reaction. There's no ionic chemical. Yeah, exactly.
So Dr. Henry, for that part of the question, do we just put non-reactive, or do we have to show like an equation? Or I know there's not an equation, but like, do we have to show something else, or do we specifically just write non-reactive?
You just write non-reactive. You just show the ions on both sides, showing that they're spectators, and it's non-reactive. Yeah. That's it.
So what will make it reactant?
If it precipitates, or if it forms a gas, or if it forms a solid, or if it forms a...
Oh, so in this case, because it just continues to stay aqueous, it doesn't form anything. That means right. No. Okay.
Yeah, if both sides of them are totally aqueous, then nothing is going to happen, right? Because, okay, so the way you look at it is, this is the way I like to look at it, right? So you have these two guys that are coming to the party, right? Over here, your ammonium sulfate and your copper nitrate is coming, copper 2 nitrate is coming to the party as well. Now, if nobody hooks up with each other, then everybody's spectators. Everybody's sitting at the party watching other people hook up, right? So nothing's happening with it. They're not doing anything. They're not changing anything. But if they hook up, then you have a couple. You have a reaction, okay? And if everybody's spectators, then you're never going to have a reaction. Nobody talks to each other. Have you ever been to a party like that where everybody's standing on the wall, looking at each other, waiting for the person to come and talk to them? I think we did that in the 3rd grade or something. Are you guys there?
Yeah.
Sorry, my kids are being loud.
Okay. So, but as soon as you start getting older and you start talking to each other, people start hooking up, right? You know, you still have those people that are spectators, those people that are just going to watch the party, right? So those are the ones that they bring their friend and they just sit there on the wall and nobody talks to each other, right? But you have those ones that actually hook up. So that's going to be your reaction. Anytime that you have somebody hooking up with somebody, forming a precipitant or a liquid or a gas, then we know that you have a product, okay? But if they're still aqueous, meaning they're all soluble, then there's not going to be a product. So there's not going to be a reaction.
So Dr. Henry, in this case, the calculation, the E, calculate the amount of precipitant produced, then that would mean... do it. Oh, okay.
Right, because there's no reaction. So how can you calculate the precipitant?
Because there wasn't a precipitant. Okay.
There wasn't a precipitant, exactly. So if there wasn't a precipitant, you can't calculate it, right?
So do you put not calculable? That's it?
Yeah, you just put no reaction. And then you don't have to do any extra work, right?
20
At
points.
that point, there's no reaction. It's intentional to make you think about problems, right? You can't just assume that everything is going to give you a reaction. You've got to show me that everything is going to give you a reaction. Right? And if you want to do all that extra work and be wrong, then hey, that's on you, right?
I think this is going to trick many people.
It is. It is. Because many of them are not going to look at the lectures, right?
Many of them are not joining your class. I'm just kidding.
Exactly. Many of them are not coming into the class. Exactly. And so that's the point of it, right? It's like, how can you learn things if you don't show, right? That's the moral of the story, right? The purpose of this class is to learn. You got to show to learn.
I have like 4 of my classmates that are always asking me, so I need to learn it so I can teach it to them. So if I get it wrong, 4 of my classmates will get it wrong.
That's right.
Brenda, so for the for the balance equation for B, you have you have your NH4 that's aqueous, and then you have CuNO3 that's aqueous, and then on your product side you have 2NH4NO3 that's aqueous, and then you have the CuSO4 that's aqueous.
Yes.
And then that you get that off the solubility chart, right?
Yes.
And that goes back down to D on there's no change or there's no reaction, so that are non-reactive.
They're all spectators because there's no precipitate being formed.
Right. And then Dr. Henry, you said that you have to show the you said you had to write non-reactive,
right?
Yeah, but how do you
guys
show
see
that?
What you have here? Like over here on the other side, you're gonna have the exact same thing on the product side, right?
It would do it. Yeah.
Let me circle this.
They'll cancel out.
Yeah. You're gonna have the exact same thing on the product side, right? So if you're gonna have the exact same thing on the product side, it's gonna cancel out.
So I just write the 2NH4 plus SO4.
Yeah, on the product side, you're going to write exactly the same thing because that's what you're going to have. You're just going to have the ions, right? And if nobody hooks up, nothing happens. They're just sitting in solution, not doing anything.
Right.
That's it. Delicious. And so let me give you guys another hint. This is my last hint. I'm not giving any more after this. I'm done. Dropping the mic. Number 8 is a very similar problem. I'm not going to say that there's no product. Even though it seems to be more complicated, don't overthink it. Okay. And then number 9 is another similar problem. Okay.
Okay. I was gonna ask you for C on number 2, where you have to write. It's down.
Sorry.
Right there. For the ionic chemical equation, you don't have to put like the state of matter, right? For every element.
You have to.
Yeah, you do, because they're all aqueous.
So
right?
you have to put AQ in every single one of them?
Yeah, because all of these are aqueous, right? So you're gonna have to tell me that.
A lot of AQ.
Yeah. And so look at it. It's a trade-off. Either you could sit there and have to do all of these calculations, right? Or you could tell me that they're all AQ, right? So then that way you don't have to do all the calculations later on.
So we could think of ionic chemical equation like the notation in math where you have to like write it all out.
Yeah.
Okay.
Yeah.
And then so you know how like I would always write the charges, and you said you don't do that on your problems?
No, you don't do them when they're together. Right?
Oh,
you don't write them when they're together. Like up here,
that's the
differential equation. They're separate, right? So what's holding our ionic compounds together is the fact that your positives and your negatives are attracted to each other. Right? But if you put them in solution and they're dissolving, then the water's interfering. Remember, water's a homewrecker.
Yeah.
It's separating. Yeah. It's separating them, right? It's keeping them separated. And so that's exactly what's happening.
Okay, yeah. So would that mean that most of these are like non-polar?
Be careful with my papers.
No, they're not polar. They're ionic compounds.
Oh, sorry.
Remember, the water, which is polar, is separating them, right?
Yeah. Okay.
Okay.
Dr. Henry?
Yes.
I have a question on the significant figures.
Mm-hmm.
When do you know to round up or not to round up?
Remember, if it's 0.5, if it's 5 and above, right?
Mm-hmm.
We're going to I should say, no, if it's above 5, we're going to round up. If it's exactly at 5, we leave it alone. Mm-hmm. But if it's below 5, we leave it alone.
Okay. I was confused about that because the other day it was like 3.5 and you did not round up the 5.
That's right. I didn't round up to 5 because it was exactly 5.
Okay.
Yep.
Thank you.
Yeah. So you're saying
it's funny because sometimes I remember my lecture notes, I have to go back and make some corrections. And also some of the things are from the book and they make the mistakes. I need to fix those. So.
Mm-hmm.
So you're saying if it was 3.4, you would leave it 3.4? You wouldn't go down to 3.0?
No. Let's say we have 3.45, right?
Oh.
Okay. And we have 2 sig figs. Right?
Okay, then it will be 3.6. 3.5?
No.
No?
3.4.
No. It's going to be 3.4.
So you only round it up if it's above 5?
That's right.
Okay. Below 5, no. 5 and below, no, to make it clear.
Okay, so this guy would be, again, you're right, it would be that. So if I have 3.502, then that one I would round up. So that would be 3.5. Because it's greater than 5, right? Because we have stuff down here. Okay.
Dr. Henry, are you recording this so that way we can watch it later?
I am recording it.
Okay, because I gotta watch it in slow motion.
Yeah, I will post it.
Please.
I'll try to post it up tonight when I get there.
Okay.
Okay.
So I'll say now there won't be any closed caption.
Okay, that's fine.
Oh, that's terrible.
Because it takes me a moment to go through and do all the corrections. Every time I say Alexis, they think I say Alexa, you know, and then.
Also, Dr. Henry, this is aside from exam 3. So were you going to provide the link for the example for the 1 page, or not the 1 page, the 2,000 word?
Yes, I'm gonna also put that up, right? I'll put that up.
Okay.
Write that down. My list. Okay. Anything else?
Okay.
Yeah.
Oh, sorry. Go ahead.
I was just gonna ask which Brenda helped us.
I believe Brenda and
We're supposed to write this, right, on our test?
Yes. Yeah. But you guys are all now here. Just take a snapshot of everybody in the chat. So just go to the chat and take a picture of it. Or if you go to participants, sorry, not chat. Doesn't it say participant somewhere for you guys?
yeah. So
Yeah, just take a picture of it because you guys were all there. Any other questions?
yes, Dr. Henry. When are we for as per the lab? Lab 11's actually the one before we did this Friday, right?
Yeah. The gas lab, I'm giving you guys all credit for because we had a lot of people who had struggles because of the equipment. We had a lot of stuff break down in the middle of that one. So
okay, so and that's the one that's due today, right?
No, the one that's due today was this lab, the one that we did this week, because we did most of it in class.
Okay.
Although there should be a spot for it. Let me put it. I didn't put that spot up. Let me open it.
Because
I mean it says 11 is due tonight.
Right, okay. But 11 we haven't even gone over it.
Yeah, so just go ahead and upload what you guys have done.
Okay, I just because
I'm giving you guys full credit for it.
Okay, production and investigation of 4 gases, that's the one we did before this week.
Yes.
One before this week. Okay.
Yes, so I'm giving you guys full credit because we had technical difficulties with that lab.
Okay, well, I mean, and for the one for this Friday, when is that one going to be due?
Apparently it's going to be due next week because I screwed up and it said that this one was due this week, or the one 4 weeks ago. So it'll be due next week, but I'm going to try to put it up tonight so I don't forget it.
Okay, I do have some questions in regards to that. Do you think you can help me?
Real quick, because
I know we're running out of time. Yeah, for example, in it's asking for number 2, it says, what generalizations can you make about the nature of the solvents that dissolved ionic solids the best? What do you mean by by generalizations?
What I mean is like, okay, so what type of solutions? Like, so what was it that caused ionic solvents, right? Or solutes, right? So let me pull up the question. See if I have that question. Hold on.
You're talking about the lab we just did?